All right, let's get started. All right, homework 1, as I post on Piazza. Connecting components will be extra credit. That ended up being more subtle and involved more fighting with AWS than I intended. That was not the goal of the problem. You can still continue to work on it. You may want to read about like connecting components in Union Find online if you continue to work on it. Try to get Cython installed. That'll be next homework, and will be necessary for a lot of stuff we do for the next while. So today, going to continue talking about multiprocessing, multithreading, and communication costs. Going to basically finish off the lecture from Wednesday. So I'm going to work through the same code again. Poll, how many people do have Cython installed? Good. How many people tried this code and it worked? All right. No, so if you have problems, talk to me now, because later on you're going to ask questions and it's going to be harder. There'll be less time to help solve them. But this code should basically work once you get Cython installed with the pix import and all that stuff, which makes it a lot easier. I encourage you, in fact, if you've already got Cython installed, to go ahead and clone this and run along with the lecture. At the end, I'm actually going to make a few suggestions for how to extend it, and I'll want to talk about that next week. All right, so the problem, we were computing the Mandelbrot set just because it's a nice dense computation. It's got a very low memory to, or very high compute to memory bandwidth. So it's a good, and doesn't have any sort of intercommunication costs between adjacent values, right? And so it's a good candidate for parallelization. And so this lecture is just about exploring the costs of communication, and then can lead into thread interaction and cache and memory. And that's what it's going to go at the end. So the serial version, right? We just took some coordinates, array of complex numbers, and then an output array, and we just call this function. I don't have the code up here. If you want to look at it, just pull it up in the repository. But it just goes through and it takes each coordinate out of the input array, churns on it for a while, and then writes out a count to the output array, all right? And so on this machine, the single-threaded, basically one out of 4 processors in this machine, though it's hard to say how many processors are actually there. There's one processor, 4 threads, or 2 cores, each running 2 threads. So no serialization, just call the function, but only run on 1 core. 200 million complex multiply adds per second. So on a 4-core machine, we would hope, without changing the low-level computation to make that faster, that we could get close to 800, right? That's our goal at the end of this, is 800, 4 times this, assuming that we actually have 4 cores. Is that clear, where that's coming from? Okay. Then we took this multiprocessing approach, right? We're going to take and we're just going to dice it up into blocks. We're going to then launch 4 workers and have them work on blocks, right? So 10 blocks on the side of the array, so 100 total blocks. So plenty of small jobs to hand off, but not so many that overhead should be a problem, right? If we chopped it up too finely, then scheduling is going to become an issue. We're going to have thousands of jobs to run, and there's going to be a lot of just switching costs. But also not so large that we have to worry about things like some workers doing a lot more work than, some worker is working inside where the counts are high, some other worker is working on the other side where it's low, and we get an imbalance in computation. We want roughly balanced computation and not too much overhead, so that's what we're aiming for with here. We then work by block, but in this case, we send all the coordinates over, right? The serialization here. What was serialized in this version? What was being communicated? What? The whole block. So all the data in the block. Right, this is before we got to the shared memory. Right, yeah, in a second. We'll get to that. So this one, we're taking all the data, we're writing it out to some description of that data, not paying attention to, not trying to do any sort of compression or using any smarts about what's actually in the array. And we're sending all the data across, reconstructing it there, computing on it, producing a result, and communicating it back. And so there's a heavy serialization cost, and we see that in the results, right? So even with 4 workers on what should be a very easily parallelized problem, right, we see better than 2 times improvement, but we don't see anywhere close to 4 times improvement, right? And this is the serialization overhead. This is the communication overhead. All right, so we're like, all right, well, this is not good. Let's take advantage of the hardware that we have. And our goal is 800, right? And we achieved 490. So let's use shared memory. All right, it doesn't cost us anything. The operating system just basically turns it into the same memory that multiple processors see. And we serialize by slice coordinates. Or we serialize slice coordinates. So remember, slices. This will matter for NumPy. This matters in a lot of cases where you're talking about shared memory, where you start talking about handles. Python happens to talk about them in slices. When you have some array, and you take some section out of it, some running total, you get a slice, or a view, it's also called. Well, you've taken slices, you get a view. Uses the same memory, okay? And we can create them outside of this format, the usual sort of indexing format this way, using the slice command. So to write, 0 to 10, we just do this. And those are just objects that have a start and end at a step. That's all that's in there. In fact, I think you can peel, I don't know if they're even implemented in C. They might be implemented in pure Python. But that's all they have. So serialization is just communicate these 3 numbers, okay? So our next step was, okay, we're not going to serialize all the data. We're going to share memory and serialize the parts to work on. So there were two little adjustments to the previous version. One, let's convert the in coordinates that we created in the usual sense, just an array, into a shared variable, so that all the processes have it. And then when we have this wrapper function, it refers to the shared variable. And so anyone that reads from it, any process that reads from it gets the same answer that any other process would get. Anyone who writes to it can see the result. Okay? Is this clear? When we get to threading, this won't be necessary. But we're trying to, get that from the multiprocessing machinery. And the other thing is then, instead of iterating over the blocks themselves, we get the slices that are the same pieces that we would have chopped out and serialized in the previous version. This one we're just going to talk about these coordinates in memory in those arrays that I'm already sharing with you. And we iterate over those. And then we just use the ij slice in the wrapper function, right? So we've reduced our serialization cost significantly, right? We've gone from 400 by 400 complex numbers down to 6 integers, right? Great. Big step up, yeah? Still disappointing, right? Good, bad. We get almost another, not quite half about a quarter of a processor is all. But still a little disappointing. Why? Why is it still so slow? We're not serializing nearly as much. Now we have to start talking about memory access patterns again, right? We've got 4 workers. They are each working on different blocks. The blocks spread out, the amount of work is pretty good. So what's the memory access pattern for these workers? How are they actually accessing the data underneath, right? Sorry, Jackson, I think I lied. Right, we're computing on, we've got an in array and an out array of the same size, right? And we're dicing it into blocks and working on the individual blocks, right? We're not passing all the data inside, but we are sending, here's one task, work on this region of shared memory. What's the individual worker going to do in this space? Looking at the code, it's just a simple loop, right? It just goes across here in this direction, and then the next line. Computes one value and writes it here, right? First of all, how does this interact with the cache? Especially when right here in one row, is it good, bad, coherent, incoherent? Am I coherent? Is everyone just dead after homework 1? Homework 2 is not going to bring you back. Now you're scared. Sorry. We'll talk about homework 1 in another lecture. Right, this is good, right? Coherent access, right? We're just going to read a value. We're going to read the next value. They're stored adjacent. The memory layout by default in C and in NumPy is these are all coherent. This is big steps, right? So this is good. And then we hit this place where it's bad, right? And moreover, we're not on cache boundaries we can't assume that we're on cache boundaries, and in fact we know we're not, right? The block size is something like 400 or something like that in this particular problem, the way it's set up. And so over here, we're probably straddling a cache line, right? So what happens is one worker comes along, fetches this cache line in, reads from it, and then doesn't use all of this. And so if it ends up in their L1 cache, the next worker comes along and says, oh, I would like that same data. They're like, well, it's over in this other cache. I have to go sideways, right, to the other part of the core. That's bad enough. At least it's read-only, and so if it can take some fast paths there where it's basically, okay, well, you can either go to this other processor, but he didn't change it. It keeps track of these dirty bits. I didn't change it, so maybe you can just go down to L2, and that may be faster. But over here, it's really bad. Worker 1 fetched in the cache line and modified it, right? Change that value. Worker 2 says, okay, I want to come in and I want to change this value. It's been modified. The only person who has a valid copy of that is the other processor, right? Does this make sense? Remember, we've got the hierarchy of caches, and some of them are shared. L2, L3 are shared, or might be shared. L1, not shared. And so if someone pulls something in L1 and reads from it, maybe okay, it's also in L2. The other processor can just read the unmodified copy. But as soon as you start modifying, especially if you both start modifying, you've got this cache contention, right? I want to write to it. No, I want to write to it. You're trying to share a resource, and it either has to stay in one processor's L1 cache, and the other one has to talk to it and go slow, or steal it, and then the other one needs to take it back. This is very bad, this behavior. And we have a lot of that, right? We're doing it all along here, and probably all along this separation 10 times across, right? So poor behavior, poor sharing. What would be better?
So BDF within the cache line?
Oh, break it up by cache line?
Yeah.
That would work? That might work. It might help some. So we've got it on the cache line. What about this transition here, right? It's okay. Probably, it might be okay, but big jumps in memory? Very good. Do you cheat and look at the repository? Okay, good. So we'll still do the same thing in this next version. We're still going to use shared memory for input and output. But instead of slicing, we're going to do entire rows. Why rows? So you get a full coherent thing. There's no, the next row is very far away. So you're going to get very little interaction between processes trying to write to the same data or read from the same data. You're going to get cache line behavior. You're going to base more cache lines across. Okay? And so really, that's a very minimal modification. We're just going to take slices that are slightly different. Instead of slicing blocks, we're going to use exactly the same machinery. We're going to use this by rows function, which produces slices the same as the other one, but instead slices the entire array by rows. In this case, we've increased our serialization work, actually. Right? Before, we were doing 10 by 10, right? 10 rows of blocks, 10 columns of blocks. So 100 total slices. And in this case, we're going to slice individual rows. And I think it's a 4,000 by 4,000 array. So is it going to pay off? All right, all we changed is this. The rest of the code is the same. Off to code land, off to my terminal. There we go. 680, right? Back to, where did my question now? 680, oh, 620. It varies. So 680 is pretty good, right? 620 is more what I usually get. That was sort of an outlier. So 620, 680, somewhere there, let's say 650. It's pretty good. Yep.
I think it helps a lot when you draw out like the physical explanation between the first multiprocessor and then the shared block when you serialize the slices. Like I saw that you're just slicing. I understand that concept, but
okay, so this one. Yep. Let me. So the first one and this one were similar in terms of how they were dicing up work, right? So we have our input. I won't draw the output. So the first one, we just call it on the whole thing, right? And it just churns away. The second one, we cut it up like this. But then when we take a block out, right? And we need to communicate that to a worker. And so you're talking about version 1.0, right? Yeah, version 1.0. We take this and we actually, if this has a 1, 2, 5, 6, 9, we say, okay, I will pass the message 1, 2, 5, 6, 9, ... to the worker. And it will reconstruct this array, 1, 2, 5, 6, 9, and process it, get a new array, 5, 10, 3, whatever, and pass that back. Actually, let me show the output. It'll pass that back, and it'll be written in right here. So the cost here of communication is I have to read this out, write a description of what's in there, communicate it to the worker, which has to reconstruct the same sort of subarray in its own memory, do the computation, pass it back, which still includes, 5, 10, the same sort of, encoding, 5, 10, 3, string. Reconstruction here, 5, 10, 3, and then copying in. The expensive operations here are not actually the copying or extraction. Extraction is basically infinitely cheap, right? That's just take a subarray, numpy that costs nothing. But converting it to a string and communication. Communication isn't even that high. But this serialization is expensive. This doesn't cost nearly as much, right? We see that we don't get anywhere near the sort of step up that we would expect. And it's because of this. Not just because of the computation, but also because we've increased our memory. The amount of memory we have to work with is 3 times or more, right? We cut this out. We wrote this somewhere to memory. We communicated it. We built another copy of it, another copy, another string, and another output. And then finally, go here. These are just sitting, all right? Version 2 is, I'm just going to give you a copy of this, okay? We're going to work from the same book. It's like instead of reading a book to you, I gave you a copy and said, work on page 5 to 10, right? So that's what happens in version 2. I give you these coordinates, or this block, and I communicate just the page numbers. And you also have your own, we have a shared workbook. We have no contention, so we're not worried, no one's working on the same block, so we don't worry about locking. And you write your results in the same place, and then we'll put it together, okay? So the
slice is just a memory address.
Basically, it's like a relative memory address. It's got a bit more information. It's a memory address plus how far to go and how to step by. Yeah. Then the problem becomes, okay, so the serialization cost is very low. But the problem now is, okay, now we don't have contention in the sense that you're not going to override someone else's work, but we do have this, well, you can only use a certain pen on a certain page, and I've got the pen, you need the pen. So that's how the cache starts to cause problems, okay? Are more questions about that? Okay, great. All right, so we're up to we're still below 700, right? But doing much better. Memory access is much cleaner. Still got some serialization, still a fair amount of serialization, right? Because now we're doing it by rows, now we got like 4,000 little messages being passed around. Still, sorry?
And if you want to see like the worst parallel like performance, you would send it by collab.
You have the code. I'm going to suggest, actually, at the end of this, I'm going to say, play with this, and let's talk about it on Piazza, and we'll talk about it next week. That's a good question. What will happen? How slow will it go? I mean, someone might have it running here. It's pretty easy to change by rows to make a by columns function and see how much worse it is. But I'll leave that for, I mean, you can, yes, that's a very good guess. That's probably the worst, or one of the worst. I mean, you could probably come up with even worse versions, but that's generally not what the class is about. Hopefully. All right, multi-threading. We're not going to get into the details right now of threads and locks and stuff like that. We're just going to hop into multi-threading. We're going to use the same slicing strategy. We're just going to replace pool with thread pool. Right? That's all that we're going to do. So we're not creating more processes. We're just creating pools. As I said before, we're on Linux or OS X. Threads and processes don't cost anything different. Right? So it's a new version, threading rows instead. What do we think? Predictions on the performance of not changing anything except the pool type. Slower? Same? Arguments for or against? I mean, the communication, yeah, exactly. Communication primitives might be a little bit different. They still serialize the same way, though. The encoding is going to be about the same. So, I mean, slower is certainly a reasonable choice as well. So, let's check. So all I have done here, actually, did I show that in the slides? Yeah, the only change is in the code where it says pool, I use thread pool, which is a slightly different import. But it does exactly the same thing. Instead of getting a bunch of processors, you get a bunch of threads, and then you still have map and apply and whatever else. So, and I don't have to do shared memory either. Right now, it's all just threading. Okay. So we were at what, 680. Slightly slower, but within the noise. About the same. I don't know where all my pictures went. I'm kind of disappointed. So let's see. Oh, wait. Yep. Yeah, okay, sorry. About the same. In fact, when I ran it before, I was getting exactly the same numbers, but it varies, up and down, between 620 and 680. So as we said, process, threads, about the same thing. Serialization is actually the same process. It's going to use very similar primitives to communicate. Okay. Let's just remove the serialization, right? The serialization cost is still very high. We expect that we should be able to get 800 from this, roughly. Let's just we have 4 threads in this case. Let's just give every nth thread the nth line to work on. Okay, so there's only going to be 4 slices. We're going to use this, this slice, which is, offset by the thread index, somewhere between 0 and 3. We'll just take the whole row, and then step by 4. How can this go well? How can this go wrong? What happens if one thread runs all the way through before any other thread gets started? What happens to my L2 cache, L3 cache? Predictions? They're going to be full of useful stuff for the other threads, unuseful stuff? Right, it's all the stuff from the last thread. Well, right. So that could be good, right? Actually, because I'm not sharing any information with them. Or if they're running at the same time, I'm going to be hitting the same, near the same memory. So it could be good, could be bad. This one you really have to experiment. to know what's going to happen. So what did I do here? Interleaved. There's a good number. There's a better number at least. 720 out of 800. Okay. It's not obvious why this is better, necessarily. Well, it is obvious. This is the serialization cost. This one's fairly obvious. The question is how much. All right, so let me get back, actually. Come back to the lecture. Okay, so basically removing all the serialization and working interleaved I rows, 720 out of 800. Probably going to be fairly happy with that because I haven't managed to make it go faster. In particular, what is it? Okay, so now we're doing interleaved rows. What's another obvious non-serialized? So basically, I just want big blocks strategy for multi-threading in this case, shared memory. I only want to send 4 block chunks of work out. This one I did every row to every nth row, every nth thread. Another choice? What's that?
4 rows, 4 rows, 4 rows. There's like you take n over 4 rows and then over 4.
So I don't have that one. It's time for live coding because I don't have that one. Does everyone understand what he just said? So instead of every slicing by rows, let's slice by big blocks of 1/4 of the rows. So that looks like actually, do I have that one? I don't think I have that one. Let's see. Right. Does that look right? Okay. Yep. And so it's underlined red. All right. Space doesn't matter, but PEP 8. All right. So blocks by rows. Predictions? Good? About the same? Faster. So what? I called this interleaved, right? Yeah, even though it's not. Oh, wrong command. Not good. Not good. Surprising, right? Almost surely, and for this we'd really have to start digging into cache behavior, but almost surely cache misses, right? Someone earlier, one of my friends in the other threading has, I'm working on hopefully, in the interleave version, they're all working on roughly the same location at a time. And so the cache is hitting, it's very hot. I hit the end of the row, someone else can use it right away. Or, associativity. Like we're working in the same place, but we're working adjacent, so we're not going to be poisoning each other's L2, L3 associativity caches. Here, no. Now we're very far away, right? And so it's quite possible that, I'm hitting part of the L2 cache and poisoning it for you. I don't know the reasons. I've started digging into it. I have to go into the performance counters and start looking at L2, L3 misses. If you're on Linux, this is much easier, actually. It's kind of where the Mac falls down. You can use the Instruments app to go after this, and it's worthwhile getting used to it, but it's still a pain even to get that. Under Linux, you can just run perf, and it says, or I think it's perf, and it says you you missed the cache this many times, you hit the L2 cache, L3 cache, and you can tell exactly what's going wrong. Well, as long as we're here, we can do your idea of columns. No, I'll leave that for you guys. Okay. We're going to finish kind of early today, but I figure after the weekend you won't complain too much. Questions for you. So I'd like as many people as possible to get this going on their machines. We're going to need Python for later on. Get the code going. Ask for help if you can't get Python going. It's possible under Windows as well. How much difference does the multiprocessing versus threading make? How fast can you get, like we played, I did some things and moved towards multithreading so I could get, take easy steps from multiprocessing to multithreading, see how threads behave. Is there much of a difference? Under Windows, there will be. It's quite probable there'll be more of a difference. Is there a better way to slice the array into 4 parts? I mean, we just tried 4 horizontal bands. That was not good, right? But maybe it's blocks of 2. Maybe it's maybe it's sublines, right? Maybe it's cache lines. Certainly, it's probably not 4 vertical bands, but I encourage you to try it to see how bad it is. Post on Piazza. We're going to discuss this at least some on Wednesday. I'm going to run some more experiments. I'm going to try and get actual like L2, L3 hit misses counts. If anyone's on Linux, then definitely look at the performance counters, because you can get some very good insight at what your code's doing. And when we get to particularly GPU programming, those become that sort of understanding of what's going on in the lowest level of memory and memory access is critical. But in general, just for all your code, if you've got an algorithm that you're working on that you're trying to speed up, particularly if it's something image-based or dense data. I mean, if you're doing graph processing, there's not much you can do. There's some tricks you can pull there. But if you're doing something that's memory dense or computation dense relative to memory, or sorry, vice versa, if you can improve your cache behavior, that is the easiest way to make your program faster. I'm going to keep hammering on that. It's going to be even more critical when we get to GPUs, where if you can keep the memory, the computation fed with memory, you can really cruise. All right. As I pointed out on Piazza, everyone gets 2 automatic late days. We're probably not going to have more than 3 assignments still at this point. That's what it's looking like. So if you're going to continue working on homework 1, continue doing so. Ask questions. We'll continue to support on Piazza and wherever else. Questions? Yes? Date of the last commit on the pull request. Does that make sense? So we only have access to it through the pull request. But when you commit to the same branch you've made a pull request from, it just stitches on that commit. So at that point we say, okay, well so it'll be based on your last commit. We'll take it on a case-by-case basis. I mean, someone's minor update is someone else's complete homework, yeah. Oh, the minor update, I changed my comments into code. So if it's minor, I mean, you can email us and ask, but it won't matter here because if you have 2 free days, I mean, it's not actually due to Tuesday. Yeah, don't worry about it. In general, I mean, if you commit Wednesday at 1 a.m., we'll take it on a case-by-case basis. If you try to abuse it, you may be sorely disappointed. The original, this is how the class has been taught. Has always been 2 late days. There used to be more homeworks. I made the homeworks longer. You may have noticed. You may not have noticed until you'd already given up the extra time I gave you. But that also meant fewer homeworks. There's some possibility that we'll add something in there, but if we do, it'll be a minor homework, and you probably won't need to worry. We may split one of the later homeworks into 2 smaller parts. But at this point, just plan on 3 homeworks, 2 late days. Try to get it done by the due date. It does tend to bias us towards your case in question, later on. But if you didn't, that's fine. You have 2 days. All right. As I said, homework. Oh, sorry. reduced by key is slower?
Yeah, you said the reverse. Well, for me,
Yeah, it should be the reverse. It depends on the it might depend on what computation. Reduced by key followed by a map? Are you ending up with the same result? So if you've got, are you doing reduced by key on a list thing, like append? This is maybe something separate, because if you're doing the same computation, reduced by key, in general, almost always should be faster because it can reduce before it does the shuffle. It can do if there is a key that's repeated multiple times in a partition. That can be reduced before it's communicated. So you get some communication overhead is removed, and it's doing the same computation, right? So in general, it should be faster, but there are ways to break this. Particularly if you're building up a list instead of just using group by key, if you're building up a list using reduced by key instead of just group by key, it's quite possible that, because list appending is slow, right, in general, because you rebuild the entire list. Well, you rebuild the later part of the list and throw away what you did, but you can be faster if you know that you're producing a list, you can hack it a little bit more. So that might be what's going on. Let's talk more about that, because it is surprising. Any other questions about homework 1? As I said, problem 5, the connecting components is extra credit. I did not intend you to have to fight with AWS as much as you have had to for that problem.
the extra credit of program 5, is it like extra?
That's like extra credit. Yes, the spot instances, we should have done this. I didn't, part of the making it to resulting in so much AWS fighting has resulted in costs being higher. If anyone has actually been charged money by AWS, please make sure you talk to them, open a case, and talk to me, and I'll help back you up on this to make sure that that shouldn't happen, and they're generally pretty forgiving of it.
I have a question. If we have another .edu address, then can we use it and have 100 more?
This is up to you. This is a moral question, I think. It could also be dangerous because how many credit cards do you have, and how many names do you have on those credit cards? Probably 1 on the names. I mean, hopefully. Again, it's a moral question, and I'm not going to get into it here. It shouldn't be necessary, though. Talk to AWS. So there's some discussion of this on Piazza. You basically put in, it's just a couple of arguments to start, right? Okay. Okay. So, if you want more advice on using spot instances, ask on Piazza, and we'll make sure that all the details are in there. It sounds like probably cloning the instance, or cloning something you've already set up before is probably the easiest way to go. Okay. More, I know, okay. Anything else? Excellent. See you Wednesday.